In this third video, we're going to learn how to test a function for multi-valuedness, and also we're going to learn how to handle multiple branch points. As a recap from the previous video, we used the example of the square root function to understand what's meant by branches of a multi-valued complex function. And we also looked at what a branch cut is, when to use it, and its relation to branch points. After watching this video, you should be able to test a complex function for multi-valuedness. And this is a really useful tool for analysing complex functions, and you'll get lots of practice of doing this in the problem sheet. You should also be able to identify suitable branch cuts to make a function single-valued. And lastly, you should be able to test for branching at infinity. After finishing this video, I encourage you to attempt the problems in the associated problem sheet. There are plenty of examples to help test your understanding. In particular, it's important to get lots of practice at finding branch cuts. And this will be important later on in the course when we're looking at integrals involving multi-valued complex functions. And with that, let's get going on this last video of topic 4.
In this video, we're going to be looking at how you test a function for multi-valuedness. At the end of the last video, we saw a couple of examples of how to make branch cuts. But in general, how do you figure out where a branch cut should go? We're now going to see that the ideas from the previous video can be extended to functions with multiple branch points. Let's look at an example of such a function. Consider f of z is given by z squared plus 1 to the half. What do suitable branch cuts look like? We can rewrite the function like this. F of z is the square root, and then we can factorize z squared plus 1 to give us z minus I times z plus I. We know that the square root of z has a branch point at z equals 0. So our values of z here that make the expression under the square root sign equal to 0, also branch points. That means for this function as written, we're asking the question, are z equals plus I and z equals minus I the branch points here? To investigate this, we need to fix some notation to describe the points z minus I and z plus I in the complex plane. I'll write that down. Fix some notation to describe some z minus I and z plus I in the complex plane. I'll draw a picture. Where we have our imaginary and real axes. And we're going to be considering some arbitrary point in the complex plane labelled by z. Our points of interest, the things that we suspect are going to be branch points, are at plus I and minus I. The quantities under the square root symbol in our expression, the z minus I and z plus I, they are going to be complex numbers, and we can describe those in modulus argument form in the following way by defining these moduli and these arguments in the complex plane. That's the angle θ1. This modulus is R1. And this angle here is θ2. And this distance or modulus here is R2. We now write that the complex number z minus I is given by the modulus R1 times e to the I θ1. And similarly, the complex number z plus I is given by R2 e to the I θ2. We can substitute these into our expression for our complex function. This now becomes the square root of R1 times R2, and then we have e to the I θ1 over 2 e to the I θ2 over 2. And we can combine those arguments together to give us e to the I θ1 plus θ2 over 2. We now have that the function at some point z is given by this expression, where we've parameterized things in terms of the moduli R1 and R2 and the angles θ1 and θ2. I'll make the point now that the ranges of θ1 and θ2 are defined so that they can be varied smoothly, and we'll see the meaning of this later once we've made a branch cut. Let's now investigate the behaviour of our function f of z as we make one complete circuit around various closed loops. Which we'll call C in the complex plane. This is going to help us spot multi-valuedness. First of all, let's consider some closed loop C that encloses neither of what we suspect will be branch points. I'll do a little diagram here. We have the points plus I and minus I. And in this first case, we're going to consider a loop that doesn't enclose either of them. So it might look something like this, where this is C. If we now consider what happens to the angles θ1 and θ2 as you move the point Z around this closed circuit C, it's straightforward to see that the angle θ1 after a full circuit returns to its original value. And similarly for θ2, it also returns to its original value. This means that our function, f of z, if we look at the expression that I've labelled with asterisk, this doesn't change. The function returns to its original value after one circuit. Let's now consider that C encloses z equals plus I, but not z equals minus I. Again, we've got our points of interest. And we're now going to look at a loop that encloses plus I, so it might look something like this. This is our new closed loop C. Using our labeling from above, we now see that the angle θ1, after the point Z executes a full circuit along the loop, acquires 2 pi. Meanwhile, θ2 is unchanged. If we put these into our function above in terms of the moduli and these angles θ, we now find that the function acquires a minus sign. And this confirms that the point plus I in the complex plane is a branch point of our function. Let's carry on with another example. Let's now look at C that encloses the point Z equals minus I, but not Z equals plus I. And our loop might look something like this. You can convince yourselves that with this loop, θ1 will remain unchanged, but now θ2 is going to acquire 2 pi after a full circuit. Therefore, we have the same behavior as the example above, where the function is going to acquire a factor of -1. This confirms that Z equals minus I is also a branch point of our function. As a final example, let's consider a loop C that encloses both branch points. Such a loop might look something like this. Well, now θ1 is going to acquire 2 pi, and θ2 is also going to acquire 2 pi. This means that the function is going to pick up 2 factors of -1 and therefore return to its original value. Hence we see that f of z changes sign if the loop C contains either plus I or minus I, but not if it encloses both. Therefore, we must choose branch cuts that prevent us from making a complete loop or a complete circuit around either one of the branch points. This is similar behavior to what we saw for the square root example in the previous video. We therefore must choose a branch cut that prevents us from making a complete circuit around either one of these branch points at plus and minus I. For example, We have the imaginary part of the input to our function. The real part, we have branch points at plus I and minus I. And we could make a branch cut in the upper half of the complex plane, like this, that goes off to infinity, and similarly in the lower half plane, a branch cut along that axis, also going off to infinity. Now these branch cuts are constraining the input to our function f of z in such a way that it will remain single valued. However, for this f of z is the square root of z squared plus 1, we saw in that final test loop in D that traversing a loop containing both branch points meant that the function returned to its original value. We can therefore choose an alternative finite branch cut. Allowing this possibility, allowing a circuit that encloses both branch points, but still preventing a complete loop about just one branch point. What does that look like? We have our branch points, and now we can make a cut like this. Such a cut still prevents us from making a closed loop around only one branch point, but we can make a closed loop around both branch points. That's valid because the function does not change value after a complete circuit. Recall earlier that I said the position of the branch cut corresponds to a particular choice for the ranges of the angles θ1 and θ2 that we use to label the complex numbers appearing in our function. We can look at a copy of the complex plane with the branch cut that we've chosen here and consider some complex number z, and we remember that we defined this angle to be θ1 and this angle to be θ2. With this choice of branch cut, the range of allowed values of θ1 is now minus pi by 2 up to 3 pi by 2. And between minus 3 pi by 2 and pi by 2 for θ2. So we've made a specific choice for the range of angles according to the requirement that the function be continuous in this part of the complex plane. You can check the allowed ranges of the angles for the cut that we made above as practice. As a last point of this topic, we'll quickly discuss behaviour at infinity. When we're talking about the point z equals infinity, we're referring to complex infinity, which is a complex number with infinite magnitude and undefined argument. And this might seem strange, but we've already seen another example of this, z equals 0 at the origin. That number has 0 magnitude and also has an undefined argument. And these two special numbers are reciprocals of each other. How do we consider executing a loop around the point at z equals infinity? Consider the function given by the reciprocal of z, which we're going to denote as zeta. What's the action of such a function? As usual, let's draw some axes. Where here this is the domain of our function. So this is the input z. Let's consider some circular region defined by a radius r. And we're considering points inside this region, which I'll shade in. I'm also going to label a few points of interest as A, B, C, and D. What happens under the action of f of z is 1 over z. We'll need another set of axes to describe the output. This is now the imaginary part of zeta, the real part of zeta. Our circle of radius r on the left-hand side is going to be mapped to a circle of radius 1 over r on the right-hand side. And the pink shaded region on the left-hand side is now going to be mapped to the region outside the circle on the right-hand side, which I'll shade. The points that I labelled are going to be moved around like this. A is still going to be on the positive real axis. C will be on the negative real axis. But B and D are going to be flipped around the x-axis. And that's because if you divide 1 by a purely imaginary number, you pick up a minus sign, as well as changing the magnitude. This is the output, zeta. We can also add the direction that such a circuit is traversed. On the left-hand side, if it's traversed anti-clockwise, on the right-hand side, it will be traversed clockwise. The left-hand side has center z equals 0. The right-hand side has center zeta equals 0, which corresponds to the point at z equals infinity. If we perform such a transformation on some arbitrary complex function f of z, then if that has a branch point at some point inside the circle, then after the transformation, the function in terms of zeta will have a branch point outside the circle. Now that we're able to talk about the point at infinity, we can use this transformation to investigate branching at z equals infinity. As an aside, the fact that we can think of z equals infinity as a single point at infinity in all directions of the complex plane is something I'm not going to cover in detail, but I advise you to look up the Riemann sphere to find out more. Let's again look at our example from above, that f of z is the square root of z squared plus 1. If we apply this transformation, and we're now looking at our function in terms of zeta, this becomes 1 over zeta squared plus 1 to the half. We can put over a common denominator, and this gives us 1 plus zeta squared to the half divided by zeta. Here it's the numerator, 1 plus zeta squared to the half, that determines branching behaviour. The denominator does not have a fractional power. When does this equal 0? Well, this equals 0 when zeta squared is minus 1, when zeta is plus or minus I. These are the branch points of f of zeta. The reciprocal of these simply gives us z is minus plus I as the branch points of f of z. And we saw this earlier when we were executing various closed loops. Therefore, this transformation has here given us the same information as before. However, here we note that zeta equals 0 is not a branch point. And therefore, that means that z equals infinity is not a branch point. What does this mean in the context of the branch cuts that we took in the example above? In the example above, the first branch cuts, and to remind you, I'll draw a little picture. The first example, we had branch cuts going off to infinity like this. So we chose 2 branch cuts running to infinity. Since z equals infinity is not a branch point, we can actually say the 2 cuts meet at z equals infinity to form a single cut. From plus I to minus I. Or as in the second example, and I'll draw another picture of that to remind us. we can instead omit the point z equals infinity. We've already encountered an example where the point at infinity is a branch point of the function. On the other hand, revisiting f of z is the square root of z, we earlier saw this has a branch point at z equals 0. Let's apply our transformation to investigate behaviour at z equals infinity. We define f of zeta as zeta to the minus a half, and clearly, by analogy with the square root of z, this has a branch point at zeta equals 0, and it therefore has a branch point at z equals infinity. This is a branch point. That means that in that example, we had to join z equals 0 and z equals infinity with a single cut. As a reminder, it looked like this. Off to infinity. And because the point z equals infinity is reached in any direction in the complex plane, we could just as well have taken the branch cut at any angle in the complex plane, as long as we remember to restrict the range of values of theta suitably. For this example, we chose theta to lie between 0 and 2 pi. I'll finish this discussion by noting that you get the same information by considering a loop around all branch points, all finite branch points, as you do when using this transformation to investigate the point z equals infinity. That's the end of this video and the end of topic 4. To recap this video, we looked at how to test a function for branch points and figure out how to make a suitable branch cut in order that it remain single valued. And we then briefly discussed how to investigate behaviour at infinity. The take-home message of this topic is we've seen that by drawing appropriate branch cuts, we can restrict a multi-valued function to single valuedness, and so it can be an analytic function within the region bounded by these cuts. We can then use the Cauchy-Riemann relations. As we shall see, the ability to do this is invaluable when integrating complex functions, and that's something we're going to encounter in a later topic. Thanks for listening, and I now encourage you to have a go at the associated problem sheet to test your understanding of the content in this topic.